Hello everyone. I'm going to do the exam 3 problems and solution number 2. So in this problem, it is about the interference of the sound wave. So just take this this interference. So here's the megaphone 1, megaphone 2, and then here is the person. And speaker separation is given by x, which is 4.99 meter, and listener distance in front of the one speaker is 3.55 meter. This is designated as L and designated as X. And the speed of sound is known, and it is assumed that this speaker and this speaker has same phase. Okay. If it is the same phase, the only factor that will affect the interference is actually the length distance, the length difference. Okay, so distance from the nearest speaker to the listener, R1, from here to here is R1, and here from speaker 2 to this listener is R2. And we can find out R2 is given by this one. This is the triangular condition. And then the path difference will give you the interference. And delta lambda path difference R2 minus R1 is given by this one. And then delta R can be obtained. And the condition for the constructive interference in phase source, we get delta is equal to m lambda, where the m is an integer. The lowest frequency corresponds to smallest positive m. The lowest frequency, we know that lambda equal to v. So lowest frequency means the minimum frequency means is here the case. The smallest positive m for lambda, so that m equal to 1. So lambda becomes delta r. And then in that case, frequency becomes delta r. So if you increase the m equal to 2, then delta r equals 2 lambda, so that lambda is delta r over 2. So that if you just plug in this one, then f is given by v over delta r over 2, so that it is 2 times this frequency, f0. So that it is not the minimum, the lowest frequency. So the lowest frequency can be happened when m equal to 1. Okay. So similar cases. Here is the one speaker and the other speaker, and this is separation x is 4.8 meter, and L is 3.05 meter. And what is the lowest frequency for which there is a minimum signal due to destructive interference? So previous case was in constructive interference. And now it's time to think about destructive. So we need to understand the first of all interference conditions, and then we could furthermore specify what is the condition for the destructive. So what we do now is x is given, L is given, velocity is given, source is in phase. So they are in the same phase, and the only difference that generate the interference is that the phase difference. Okay, phase difference is the same as before, and it's given. And here comes the destructive interference condition, and that this is m plus half times lambda. M is 0.012, etc. The lowest frequency or largest wavelengths use m equal to 0, and then lambda becomes 2 delta r, and then we get wavelengths and the frequency. Okay. 61. An animal emits an echolocation wave. That means it's by the reflection, we call it echo, and that by detecting the reflections, they are trying to find the locations, like a bat. An animal emits an echolocation wave if an obstacle is 100 meters from the animal. And how long does it take for the echolocation wave to make a round trip between the animal and the object? So here is the animal, and here comes the object. It's like this. And once again, Exam3 requires memorizing some formulas. So in this case, this is the water, liquid. So in the case of liquid, sound wave is given by this one. P is bulk modulus, and rho is density. And then if you plug in, you find out the velocities here. So now once you find the velocity, then the round trip distance is given by 2 times d. And goes here and it goes back. So that overall round trip is a 2d. And then time for the round trip is round trip distance divided by the velocity. Okay, right? Distance divided by the velocity will give you the time. And a nylon string is stretched between the two rigid columns such that the tension in it is 175 Newton. Okay, hence the tension is given. The string is of length L equal to 2 meters and has cross-sectional area that varies with the distance AX is given by this one. Okay. So that means if x equal to 0, because AX looks like certain value here, and then it is increasing. It's a function of x. So thickness is increasing with x, right? Determine the time takes for a transverse pulse in the string to travel from one end to the other. Okay, so that means this is that we have two columns, and then we have a string. And then we have a tension, and the length. Then we have AX, which is the cross-sectional area. And then we have a density of an oil is given, low. And then as you might know, the velocity in a string is given by square root of the t times mu. Mu is the linear mass density. Is kilogram meter, something like this. And then this case is the area is changing. Area is changing. That means your linear mass density is changing because you have a volume mass over length cubic. Area is length square. Then we get mass divided by the length, which is this one. So we get position dependent linear mass density given like this. And then for this linear mass density, the wave on a stretched string will be given as a function of t and x and rho. Okay? And then time travel or pulse across the non-uniform string this might be a little bit tricky though, but if you think about v is dx over dt. Now the v is function of x. So in this case, we arrange this one. dt is given by dx and vx. And then if you just integral, and this becomes t. And we have a 0 to L dx over vx. And then this is nothing but this form. And then what we need to do is to change the variable. Let u is 1 plus x over L. Dx is L times du. Okay. And then this integral range. So when x equal to 0, if you put x here, u equal to 1. When x equal to L, u becomes 2. So you have a range is changed for the function of u. And then this becomes very simple functional form. And then you can get this value. And if you plug in L equal 2 meter long, then you get this integral. And then this integral is shown here. And then numerical value for the time is given by t is this square root times this integral. This square root times this integral, and you can get it. So in this problem, what is important thing is that the first thing is the system is providing position-dependent linear mass density. And then by a formula for speed, local wave speed on a stretched string, you get the tension divided by the linear mass density, and then it's square root. So this is the formula, what we have learned. And then we note that velocity is function of the position. And then we want to find out the time that will take from the 0 to L. And then it is integral form, and then we can get the time. So in this case, the tension in a thin cable of a length 3 meter and the mass of 0.6 kilometers stretch between the two poles. Once again, you have two poles. And the tension is given. Due to the wind in the air, the cable is vibrating, produces a standing wave 2 times its fundamental frequency. Standing wave. So what we want to know is that here is the given. Length is given, mass is given, tension is given. The observed standing wave is twice the fundamental frequency. So that means it's a second harmonic. So first thing we need to know is that what is the mass density? Because it's a string, we need to know the mass density and the tension to find out the velocity. And then fundamental frequency, both ends fixed, is given by F1 is V over 2. Fundamental is given by the 2. And then it's a round trip. And then you get this hertz. And the frequency of a second harmonic is 2 times F1. Okay, 2 times F1. So note that why this is happening here is that if both ends are fixed, that means, okay, like this. That means if this is the L, you get, so this, if the both ends are fixed, then L becomes lambda over 2, right? Right, this is the L, this is the lambda. And then lambda is given by V over F, okay? And such that what you can get lambda is 2L, and then frequency is V over 2L. Okay. So here is the case. What is meant by the fundamental frequency for the closed, both ends closed. Okay, here. And then the displacement should be 0 at these ends, so that the first harmonic, the wave should have this kind of a configuration, okay, such that this is the lambda and this is L, then we get this condition. This is the very important assumption, and then from this we get the relationship between the velocity and the L and the fundamental frequency. V is given by tension and the linear mass density. And then the question asks about the second harmonic. That means it's 2 times F1. Okay. Problem 69, a transverse harmonic wave with amplitude of 2 millimeter and a wavelength of 1.65 meter travels from left to right along a long horizontal stretched string with a speed of 29 meter per second. Take the origin at the left end of the undisturbed string. At time equal to t equal to 0, the left end of the string has its maximum upward displacement. Find the magnitude of a transverse displacement of a particle 1.4 meter to the right of the origin. Okay, so here is the x here, and then here's the origin, According to this, at t equal to 0, left end of the string has its maximum upward displacement, so that it has a certain maximum, and then it should go like this, something like this. So let's try to summarize what we did know. So we have amplitude is given, wavelength is given, speed is given, uh, oops, left to right, left to right, and at equal to 0, left hand x equals 0 has the maximum upward displacement. And then by doing combining this information, we can say that yxt is given by this one, and maximum upward displacement x equal to 0 at t equal to 0 means, so x equal to 0, t equal to 0, is should be plus a, okay? And then if you put the 0, 0, then you can get the cosine phi should be 1, such that phi equal to 0, okay? So we have this, these solutions. And then from this, we can find out wave number and the angular frequency is given by this formula, and frequency is given by this formula, right? This is nothing but lambda f equal to v, right? And evaluate the x equal to 1 point meter and the t equal to 0.0595 second. Plug in this value here, and then we get this value. So in this case, what is important thing is that we have to come up with a right function. So in this case, from the initial condition and the boundary condition. Initial condition means is that t equal to 0, and the boundary condition means is x equal to 0. And then we get this function. And then right after this, we need to find out k and omega, okay? K and omega from the known values. And obviously, k can be found directly from the lambda, because k is 2 pi over lambda. And the omega is given by v times k. Now we know the k, we can plug in the k, and the velocity is given. Okay, so that we have a velocity, and then now we know the k, and then we get this omega value. And then we have a complete description of this wave, okay? So I'll stop here, and then I will continue later on.